So, thermal efficiency, I just want to formally define thermal efficiency. It's one of the efficiencies we'll talk about. The implications of the first law for a closed system, which I've said before, but I want to restate it. We'll talk about the efficiency of a heat engine, which is what we think of, maybe, so we're exploiting a heat difference to generate power, and also a refrigerator and heat pump. And that's what we'll do. Go I say. All right. We know that for a closed process, okay, Q minus W equals delta U. And we know that for a thermodynamic cycle, so by the time you go all the way around, there is no change in U at the end of having gone all the way around the cycle. Okay? So from that, we get Q, and this is the net. So this is any heat in and heat out, equals work, and this is any work in, work out. Okay? So for a heat engine, the more heat you can put into the engine and not lose heat out of the engine, the more work you get out. So, and that works on a power basis as well. So that's on a total basis or also on a power basis. Now, Q net, we can have an equation for that, is however much heat you put into the system minus however much heat you draw out of the system. And heat comes in at the high temperature and leaves at the low temperature. So this is QH and QL, which have been introduced before. In some texts, QL is QC for cold, so high and low or hot and cold. And work net is work out minus work in. You'll often have to put work into a cycle to get it started. And so the work net is the heat in minus the heat out, which is not necessarily intuitive. And you know, there's some complicated equations relating to work, so for an isentropic and an isothermal process and so forth. You don't need those if you know the heat in and the heat out. So you don't need to do crazy integrals to work out what your net work is. You just say, well, how much heat am I putting into the system? How much heat am I taking out? The rest must be coming out as work. So that can simplify our solutions somewhat. When we talk about efficiency, I think of efficiency as being the thing that you want out divided by the thing you have to put in. So what do we want out of a heat engine, for example? I've said at least 3 times this lecture. Work. Yep, so you want work out of a heat engine. What do you want out of a refrigerator? I'll talk about heat pumps soon. Strangely, you don't want heat out, but that's okay. What do you want? What's the flow that you're measuring as being a good result? It gets cold, that's good. Yep, so the heat out of the cold space is what you measure as what you want out of the refrigerator. Heat pump, over in Western Australia, I haven't seen any in New South Wales, but over in WA, when I lived over there, my place over there has a heat pump water heater, okay? So if you've got a normal electrical water heater, then you've got an insulated tank with an electrical wire running in it that curls around a bit and then comes back out, and you run current through the wire. It makes the wire hot, and that heats the water up. Okay, and so if you put a kilowatt of electricity through the wire, you lose that through the resistance in the wire, then the water has a kilowatt of energy added to it, and it gets hotter. Right? So that's a normal way to do things. Very simple construction, and it has an efficiency of 1 or close to, and loses some heat through the insulation. They're slightly warm. If you've got one at home, touch the outside, it's slightly warm. Gas is somewhat similar. You burn a gas, and it makes it hot. My heater over in WA is a heat pump heater, and so what that is it's like a refrigerator bolted to the outside of my my water tank, right? It draws in atmospheric air, it makes the atmospheric air colder and spits it back out. So when you feel it, it feels cold, and the heat that it extracts from the air is what it puts into the water, as well as the electrical power that it consumes goes into the water. And so it can be 2 or 3 times more efficient than a standard resistance-based water heater. It's more expensive to build because a wire is really cheap, but a refrigerator is more expensive. So it's more expensive to build, maybe more parts to break, but the promise is higher efficiency, and particularly in Western Australia, where you've got lots of ambient heat in the air, particularly over summer, to exploit, heat pumps are a great idea. So the things we want out of a heat engine, we want work out of that. A heat pump, the thing we want out of a heat pump is the hot space to get hotter, and the thing we want out of a refrigerator is for the cold space to get colder. And what do we put into them? Into a heat engine, we put a thermal difference, a difference in temperatures, and into a heat pump and a refrigerator, we put work. So into a heat engine we put Q, and into a heat pump and a refrigerator we put work. The efficiency then of a heat engine, so ETA, efficiency, is the work that we get out of it divided by the heat we have to put into it. Which we know the work we put in is the work that goes into the hot space minus the heat that goes into the hot space minus the heat that comes out of the cold space. And so we can develop an expression for efficiency, remembering efficiency is what we want is work, but we've developed it entirely in terms of heat. So this is our heat for a heat engine. For our refrigerator, and it's efficiency, but we'll call it coefficient of performance, and there's a reason we'll do that. What we want out is we want heat to come out of the cold space, so that's what we want. What do we have to put in? We have to put in work. We think about this as putting in electricity into the compressor, but it doesn't have to be electrical energy. You could imagine someone riding a bike or something, so it's just work put into the unit. We can express work in terms of heat, and so we get an expression for the coefficient of performance for a refrigerator just in terms of the heat in and the heat out. And similarly for a heat pump, and this is on the right hand side is our depiction of that. So we've got our low temperature reservoir, like the space inside our fridge. We extract heat out of that. We put work in, and then we reject heat to the hot space. You should be aware that refrigerators don't destroy heat. They move it from the inside of the fridge to the outside of the fridge. In the unit that I'm living in now, someone's installed an air conditioner, and we've got like an underground garage with a set of stairs going up, and they put the compressor for the air conditioner on the wall with the fan facing the doorway, and then the stairs go up, right? Heat rises, hot air rises. So when they're running their air conditioner, everyone else's units get hotter. It's really annoying. It's like, and their unit also, because the heat will leak into their unit. If you put a refrigerator in a room with the door open, the room gets hotter. The room doesn't get colder. Anyway, whatever. People are personally optimizing and they don't care about other people, in my experience. So it should be obvious to you, maybe not obvious, but you should be able to see that whatever heat you put in here, plus whatever work you put in here, the sum of those two values, so if this was 1 unit and this was 3 units, okay, going into the cycle, then what comes out of the cycle must be 4 units. So this is kilojoules, kilowatts, megawatts, doesn't matter, right? Because whatever comes in, if this is to be a steady state system, so it's not getting hotter over time or colder over time, then for energy balance for energy not to be created or destroyed, okay, what comes out must be the sum of those two values. And so in this case, just the coefficient of performance of the refrigerator would be 3 divided by 1. So you get a COP of 3 in this case. If you wanted this to be a heat pump and what you cared about was making the hot space hotter, then the coefficient of performance would be what you want, which is the 4 units, divided by what you put into it, which is 1 unit. So the coefficient of performance of the heat pump would be 4 in the same situation. So indeed, heat pump, what we want is heat out, the heat to the hot space. What we have to put in is work. We denote that gamma, and there's an equation for that as well. And we find that, God bless you. two things. One is these efficiencies, what we could call efficiency, are often greater than 1. In fact, you don't run a heat pump if you can't get an efficiency greater than 1. You just use an electrical resistance wire. And so we call them coefficients of performance. So, because we like to think of efficiency as being a number between 0 and 1, something we can turn into a percentage. So we don't call them efficiency, we call them coefficient of performance. And we find that the coefficient of performance for any heat pump would be the coefficient of performance of a refrigerator in the same case plus 1. Because you're dividing throughout by work, and for the heat pump case, the work is going into the hot space as well. So we find that we've got an additional unit. And that was the case before. We can see it trivially. If I could get something with 5 and 1 there, this must be 6, right? So the beta for this system would be 5 divided by 1. The gamma for this system would be 6 divided by 1. The gamma would be 1 more than the beta. So this is efficiencies, this is thermal efficiencies and thermal coefficients of performance. And there are limits to how efficient you can get, and we'll talk about that when we talk about the Carnot cycle. Excellent. The gamma is the coefficient of performance of a heat pump. So gamma is for the heat pump and beta is for the refrigerator. So refrigerator, freezer, air conditioner that's making things cold, we consider that all to be a refrigeration cycle, right? Heat pump like my hot water heater, a reverse cycle air conditioner that's making the space hot, okay, heat pump. So that's thermal efficiency. Eta is efficiency of heat engine, so you're taking hot and cold space and producing work or power. Excellent.